Hi, I'm Gary, and I want to show you how I use Cloudy. Today we're going to talk about stopping criteria. This is our friend, the M16 Pillars of Creation, and we've been thinking about a zoom into the ionized layer on the surface of molecular clouds. When O stars are born, they're very short-lived and they don't stray very far from the birthplace. So the O star is close to the molecular cloud, creating this ionized layer. We see this geometry in accretion disks of AGNs and planetary nebulae. It's a geometry we're thinking about. Complex geometries are made up of a set of simple geometries like this. So cloudy follows a ray of light shown here as an arrow in red. It goes in the direction, follows the photons from the star into the ionized layer into the cloud. The simulation we had set up stopped when we reach the hydrogen ionization front. So the hydrogen ionization front is this layer where the gas stops glowing and you get into the dark molecular cloud back here. The molecular cloud can be of interest as a PDR, the photo dissociation region, and a molecular cloud. If you're working in the mid-infrared, the PDR can be quite bright. If you're working in the radio, the rotation lines of molecules can be very interesting. So you can plow right through the ionized layer into the molecular cloud if you choose to. So cloudy is not. It has a set of default stopping criteria and stopped when the first one was met. So if you look at the geometry, clearly there's a lot going on. So we we modeled this thin shell, but gosh, there's even more material that we didn't model. And if you use the right kind of telescope, JWST, ALMA, you'll find lots of fascinating things are going in that dark silhouette. So let's think about how to extend our calculation and go down into the molecular cloud. So we're marching along. We stopped at the ionization front. Cloudy was originally designed to work with ultraviolet optical FUV data. And so cool gas, 1,000 degrees, 5,500 degrees, does not emit in the optical or in the UV. So there's no reason to keep going. If you look at cooling curves for the interstellar material, you find that there are several places along the cooling function that have inflections where two solutions are possible. The more notorious of these is at about 4,000 Kelvin, where cloudy chooses to stop. We will extend our M16 model to go beyond the H plus layer into the atomic and molecular gas in the next video. But today we're going to talk about what we have to do to think about to do this. What we have to think about is the stopping criteria for the code. So the code has to stop for some reason. You didn't unplug the computer. There's an entire chapter on stopping criteria, and the very big black lettered section 2 is danger. You better understand why the calculation stopped. There's many different reasons. If you set up 5 or 10 different stopping criteria, it will stop when it reaches the first one. So you could say stop temperature 500 Kelvin, stop temperature, stop column density 10 to 23, stop Lyman continuum optical depth 100. So it has this list of stopping criteria, and when the first one is matched, it stops. And so you have to understand why it stopped. It could also stop the calculation because of convergence problems. So that's unintended. So understand why the calculation stopped. This is the tail end of our existing M16 simulation, and it shows in the second line after the last zone the reason why it stopped. So we have here the tail end, the copper and zinc ionization is the last zone result in the M16.out file. And then the first line of text after zinc is the title that we set for this model with the title command. And then the line after that, with this arrow pointing, is the reason why it stopped. So you should make sure this is a valid reason. The calculation stopped because the lowest temperature, the default lowest temperature was reached. So that's 4,000 Kelvin. So understand what happened, make sure it's an intended reason. If it stops for a convergence problem, uh, you might want to contact us or think again about the model. Easy goes over many different stopping criteria, so there's a lot of different options. The reason our M16 stopped is because it reached the default lowest temperature. So there's a stop temperature command. You can turn off the temperature criterion. So if you want to go down to the CMB, the code will do that. You would say top stop temperature off. The temperature can be changed here if you're thinking about very hot gas and you want your cooling flow to stop at 1,000,000 degrees. You could say stop temperature 10 to the 6th. You can specify the column density. The column density is number of particles per cubic centimeter along a ray with unit centimeters minus 2. You can specify different species. You can stop at the H naught column density, H plus column density, CO column density, the column density of C2 in the first excited state. You can specify many different things. So stop optical depth is the rate to transfer optical depth through the cloud. Observationally, there's probably no reason you would set this. It's a rate to transfer property that is interesting for testing. Related to optical depth, you can also stop at a visual extinction, A sub V. So many PDR SIMs, if you look in the published literature, stop at an AV of 10 magnitudes or 20 magnitudes. So you could do that. There's two different ways to measure an AV. For a point source like a star, using the point option. So most published A sub Vs would be for a point source. For an extended source like M16, the A sub V is smaller for a given column density. So you can specify one or the other. You can stop in the thickness. So thickness is the distance from the illuminated face to a point in question, and you can set that. Stop at a radius. Radius is the distance from the star to the illuminated face. So you can say start at 1 parsec, stop at 2 parsecs. You can stop at a certain zone number. We use this for debugging. I can't think of any reason why you'd use that in a real calculation. So understand the stopping criteria. And with that, next time we're going to make a model of M16 that includes the PDR and molecular cloud and have a look at what we get.